Hello, this is mathjazz from Almost Cool. This is the 6th video in our trigonometry review series. We are going to talk about graphing functions today. Now to do that, we're going to first have to remember back to the table we had in the previous video where we calculated what we called our reference angles for all of our trig functions. We're going to do sine first, so we'll look at the sine column, and I have here our chart, or just the two lines of the chart that we care about right now, our theta and our sine of theta lines on our chart. So this tells us if these values are put into sine, these are the values that come out of sine. So we're going to use this and our unit circle to determine what points to plot so that we can connect those dots and create our sine curve on our graph. So the first thing we remember is that sine in the first quadrant of the unit circle is positive. So that'll be between x equals 0 and x equals pi over 2. Sine in the second quadrant will also be positive. That'll be between x equals pi over 2 and x equals pi. And the next thing to remember is that sine from 0 to negative pi will be negative. So we take these values here and we're going to repeat them in the four quadrants, remembering that when we plot points in the third and fourth quadrants, we're going to have sine be negative. That'll be the y-coordinates of the points will be negative rather than positive. If we do that, we get something that looks like this. And I'll clear some space on the screen. We get something that looks like this. And I'll blow it up a bit. Here we go. So we have the point 0, 0 is here. The point pi over 6, 1/2 is here. And so on to get all of our points on our reference angle chart here. All of the points on our reference angle chart here. And then once we get to this point, we reverse the order to come back down. All of our points will be positive still because now we're in the second quadrant from pi halves to pi. And if we go the other way, we get the fourth quadrant here. And see, we hit these points in this particular order: 0, pi over 6, pi over 4, pi over 3, pi over 2. We'll hit them in reverse order here: 0, negative pi over 6, negative pi over 4, negative pi over 3, negative pi over 2. Remembering that in the fourth quadrant, all of the y values will be negative. And this will be the third quadrant here. And again, we do the same thing we did to graph the second quadrant. We reverse the order of the points to get all the way back down to the x-axis, which will be theta equals negative pi, and sine of negative pi equals 0. So this is negative pi 0. So we have this graph here. This is the basic sine graph. This is the graph of sine of x. But we also have to remember that all of the transformations that we learned to be able to transform our functions apply to trig functions as well, because trig functions are functions. So we'll talk about the graph of generalized sine functions. So it'll be graphing a sine of 2 pi times x minus phi over p plus b. And what we mean by these different variables we've added in here are a is a vertical stretch, because a is the coefficient on the outside of the function. P is going to be the period of the trig function, and since the x is being divided by it, this will correspond to a stretch or a compression, because it's a coefficient on the inside of the function. Phi will represent a horizontal shift left or right, for the same reason that subtracting or adding to the inside of a function will shift the function left or right. And B is going to be a vertical shift, for the same reason that when you add to the outside of a function, your function moves up and down. Now, we've added a 2 pi in here, and we've decided to divide by p instead of multiply by our constant inside, because this gives us a very, very concrete geometric meaning for each of these variables. Phi and b are going to be the same as usual. It's shifted b units up or shifted phi units right, but a is going to be called the amplitude, and it will represent the distance from the top of a crest on a sine curve, that'll be up here at this point, down to the midline of the sine graph. So for this graph, that happens to be the x-axis. So half the distance from the highest point to the lowest point is A, or the distance from the highest point to the middle of the curve is going to be A. P is going to be the distance from either a trough, like this, the lowest point on the curve, to the next lowest point, the distance from a midpoint, skipping one midpoint and hitting the next midpoint, or the distance from a peak to, and it's not on the graph, but another peak. That's called the wavelength of the curve. That's the amount of distance it takes for the curve to go through a complete cycle all the way to the bottom, all the way to the top, and back to where it started. So now that we see this, we've seen this graph, let's play around with what this would look like. So let me put another graph on the screen. So this is a graph that we can play with. The values of A, P, Phi, and B are listed here on the screen, and we can change their value. So if I increase A, I notice that my regular sine curve stays down here at with an amplitude of 1. A equals 1, amplitude is 1. But now that I've set this amplitude to 3.52, my yellow curve, which is the one that's being manipulated in this graph, has a much larger amplitude. The blue curve has an amplitude of 1. The orange curve has an amplitude of about 3.5. And if I make A negative, it flips the graph the other direction. Here's an A of -5. P changes the wavelength. So right now we have a wavelength of 2 pi, but I can increase that to a wavelength of about 15, almost 16. And we notice that now it takes a lot longer for the curve to come back to its initial starting point. So to complete a cycle is now taking about 15.7 units of length rather than the 2 pi length that we started at. We can shrink it the other way. The graph now has a very short distance for one complete cycle on the graph. Phi will shift the graph. We need to increase our wavelength a bit to get a bit more resolution. But as I move phi, as I increase it, my graph will move right. As I decrease it, my graph will move left. Conversely, if you wrote the equation with a plus sign there, if you used addition there, then having a positive phi would go left and a negative phi would go right. So you have to pay attention to that negative sign. Since I have put a negative sign here, positive phis go right, negative phis go left. If I just left it as an addition sign, it would be the opposite. And then with b, if I increase b, my sine function goes up. If I decrease it, my sine function goes down. And this is how we will graph sine functions. So we can graph our points, and then we can perform the stretches and compressions and translations and reflections that we remember from being able to do those transformations on functions. We can do those to sine, and in fact we can do that to all trig functions. So this is how to graph a generalized sine graph. And so we can do the same thing for all of our functions. So we just remember, for example, for cosine, let me get some cosine points up here. This is the line in the graph, or sorry, line in the reference angle chart that refers to the values that cosine obtains. And we can use the unit circle the same way on cosine as we did on sine, remembering that cosine is positive in the first and fourth quadrants and negative in the second and third quadrants. And we can get a graph of cosine, like so. Notice that for cosine, instead of passing through the point 0, 0, we pass through the point 0, 1. Basically, a cosine graph is a sine graph that's been shifted to the left by pi over 2. So we can see, we can actually see that on our manipulate cosine graph that I'll put up in a bit. But these points can all be obtained using the unit circle to determine the sign. That's S-I-G-N, not S-I-N-E, sign, to determine whether it's positive or negative. And we can use our reference angle chart to determine the size of the y values. That is the absolute value of the y values. So if we know the absolute value of the y value and whether it's positive or negative, we can graph the point for our cosine graph. So the same way that we were able to manipulate the sine graph, we can manipulate the cosine graph. Make it bigger. So here we go. We can change the amplitude. We can change the period. We can change the phi is what's called the phase shift, and b is what we call the offset. So we can change all of these variables and graph the curve wherever we want, basically on this graph, using proper A, B, phi, and P on our generalized cosine curve. And we can do this for all of our trig functions. We'll do tangent next. We know how to look up the points on the chart and use the unit circle. The unit circle says that tangent is going to be positive in the first and third quadrants and negative in the second and fourth quadrants. So when we do that, we can get our tangent graph. It will look something like this. We have our asymptotes here at pi over 2 and 3 pi over 2 and 5 pi over 2 and negative pi over 2 and so on. The period of tangent and the period of cotangent is pi, not pi over 2. So in our generalized tangent and cotangent graphs, we're actually going to have a slight modification. So let's take a look at that. For our general cosine graph, and our general sine graph, and actually for secant and cosecant as well, we have a 2 pi here. If we can rewrite our trigonometric function with a 2 pi times x minus phi over p, we know that p is the period. This is not true for tangent and cotangent. For tangent and cotangent, we have to have a pi there instead of a 2 pi. Like so. Oh, there's an error on the slide. This should be a single pi by itself. But the reason that tangent and cotangent need to have a pi in this position in the general equation instead of a 2 pi is because the period of tangent and the period of cotangent is half that of all of the other trig functions. So we'll remember that the general form of cosine is like so. For every trig function except tangent and cotangent, you just replace cosine with whatever trig function you're looking at. But for tangent and cotangent, not only do you have to change this to be tangent or cotangent, but you also have to delete the 2 to get the general form. Once you put your equation into your function into general form, then it tells you the amplitude, the offset, the phase shift, and the period. And then you can graph your trig function accordingly. So these are kind of fun to watch. So let's animate this. Yeah. With a negative a, it flips the direction of the tangent graph. It's pretty fun to watch. So that's how a tangent graph would look. For a cotangent graph, our asymptotes will change direction, and our asymptotes will change position, and the curve itself will change direction. Let me delete the extra graph from there. So this is the cotangent graph. The tangent graph started each strip, that is each one of these sections. Let me blow this up to be larger. Each one of these pieces of the tangent graph, it started on the left side at the bottom, and then left going up to the right side. So it went up diagonally to the right. Cotangent goes down diagonally to the right instead. And its asymptotes, instead of being on pi over 2 and 3 pi over 2 and 5 pi over 2 and basically pi over 2 plus or minus some multiple of pi, cotangent's asymptotes lie at 0, pi, 2 pi, 3 pi, negative 2 pi. It lies on multiples of pi. And again, it goes down to the right instead of up to the right. So, and again, if we change these values, we'll get stretching to occur if we set the period as a large number, compression, horizontal compression if we set it to be a small number, and we can shift the graph up or down or left, or I guess left or right, as we choose these coefficients to be whatever we choose them to be. We can read off of our chart, our last 2 columns are going to be the secant and cosecant columns. So we have our secant points, and let's put our cosecant points up there as well. These 2 parts of the chart. Complex infinity is Mathematica way of saying undefined. So if we remember, secant and cosecant were undefined in these parts of the graph for these angles. We can use the unit circle to determine where secant and cosecant will be positive and negative. Remember, secant is positive and negative exactly where cosine is positive and negative. Secant and cosecant are multiplicative inverses of each other. That is, 1 over cosine equals secant. So that means that when cosine is positive, then secant is positive. Where cosine is negative, then secant is negative. So secant is going to be positive in the first and fourth quadrants and negative in the second and third. Cosecant is going to be positive in the first and second quadrants and negative in the third and fourth quadrants. So if we graph each of these, we'll look at these graphs one at a time. Our cosecant graph has asymptotes at multiples of pi, just like our cotangent graph did. It also, it's positive in the first and second quadrant and negative in the third and fourth quadrant. Secant, on the other hand, is going to be like tangent. Secant has its asymptotes at pi over 2 and 3 pi over 2 and 5 pi over 2 and so on. It's positive in the first quadrant, which is here, and the fourth quadrant, which is here. And then it's negative in the second quadrant and the third quadrant. So just like cosine was a shift of sine, we can see that cosecant is a shift of secant. We can, let's see, if we can set this at, let's set this at pi over 2. Pi over 2, and we click. Notice how we've shifted this graph over, or we shifted it in the wrong direction. Let's shift it over negative pi over 2. There we go. Notice that the yellow curve is now positive in the fourth quadrant and the first quadrant, and negative in the third quadrant and the second quadrant, just like our cosecant, our secant graph down here. So shifting the cosecant graph to the left by pi over 2 gave us the secant graph. And we can watch these. Notice the amplitude is going to change. It's kind of weird to think of this as an amplitude, but the distance between these lowest points and these highest points, the vertical distance is equal to twice the amplitude. So the distance from this lowest point here on this chunk of the graph to the midline is the amplitude. And so increasing A increased the distance from the midline to this trough here. P stretches horizontally or compresses horizontally. That was very effective. Here we go. And phi will move us left and right, and b will move us up and down. Just like for the other trig functions, just like all functions in general. So, thanks for watching this video. I hope that you are able to feel more confident about graphing trigonometric functions, especially since it isn't so hard once you have the reference angles and the unit circle memorized. So, thanks for watching. I hope you have a great day. Goodbye.